Hi, I'm Amory Lovins. Welcome to our passive solar banana farm, 2,200 meters up in the Rocky Mountains of western Colorado near Aspen. This was a 1983 owner-built project, took about a year and a half, and it's in a climate that at that time used to go as low as minus 44 Celsius, minus 47 Fahrenheit, about the end of each year. You could get frost any day of the year. We've had it on the 4th of July. You could get 39 days of continuous midwinter cloud, so it's not an easy climate, but this is a passive solar, net positive house, indoor farm, and research center. And we'll take a look at the outside and then the inside in a minute. This is high desert. There's about half a meter of precipitation here. Things grow very slowly in a very short growing season, so up on the hill, those old junipers are about 1,000 years old. There are some 2,000 or 2,500 years old over in the next valley, about 5.5 meters in circumference and in very good shape. But we wanted a house that would look as if it grew here. And I can't quite say that of the carport, which was a recent addition, but as you'll see, the house itself has a little different aesthetic. The two electric cars here are, of course, recharged off the 18.5 kilowatts of rooftop photovoltaic, so we're a large net exporter of electricity most of the year. We also have this carbon fiber hypercar, an i3 from BMW, recharged by this device, which has a beta circuit looking every second at the grid frequency and adjusting the charging rate according to whether the grid is short or long electricity. So I'm actually dispatching 7 kilowatts of fast grid regulation to the Western Interconnect, and if the Interconnect knew that I was providing this valuable ancillary service and paid me what FERC says it's worth, we'd make an extra few dollars a day recharging this car off the roof. Now, as we come in through the gate, modeled on the Sanctuario de Chamayo in New Mexico, let's enjoy the garden while we can, because it's now early September, and in another 2 nights we're supposed to go to minus 7 Celsius, our first hard frost of the year. I'm sorry you missed the apple blossoms that are nice to sit under in the spring, but you can see the general shape of the building. There's a large east wing where Rocky Mountain Institute was incubated for its first 18 years. Then there's an 85 square meter tropical jungle that we'll see in a minute from the inside. Then there's a living and dining wing with a utility room behind it, behind the front hall. And there's a small bedroom wing up on the west. That was where I tried a rather adventurous bit of design. I didn't know whether it would work, but it did, and that is when the big storms come over from the northwest in the opposite of the direction we're looking in, the massing of this wing makes a bit of a vortex to help scour snow off the walk, so we didn't shovel quite so much. Here we get to meet my wonderful wife, Judy Hill Lovins, a fine art landscape photographer. You'll see a lot of her beautiful work around the building and some of mine.
Hi, and welcome.
Thank you. And we'll also see a little later what that metal fin is doing up there. But for now, let's come on in and meet the family. It's a little unusual. We have rather a lot of taxidermically challenged orangutans. And they're just sort of dripping from the rafters all over the place. And the reason we have all those orangutans is, as you will discover, there's a banana jungle in the middle of the building, and occasionally we have a banana emergency where all 6 trees fruit at once. That's a 1/4 ton of ripe bananas. So we eat them, we freeze them, we bake a lot of banana bread, we give them away, we hide them in visitors' cars, but with a 1/4 ton of bananas, you really need to have some help. So we can call these guys out after midnight and they come alive and kind of like a night at the museum and help us out. Now, this is really Banana Farm 2 because Judy led a major renovation over some years starting around 2008 or 9. For example, changing all the lights to very accurate and warm LEDs. This image she did in Canyonlands. I don't know whether that's sitting up there, Schroeder with big hair on the pipe organ or me on the laptop, but this image of Dead Horse Point looks better with 12 watts of LEDs on it than it did look with several hundred watts of incandescence in her old Aspen gallery. And now looking around, you start to see what really makes the building work without a heating system. And that's a little unusual because all but one of the engineering textbooks say that if you're in such a cold place, you should buy just as much insulation as will pay for itself out of the saved heating fuel or heating energy over the years. Sounds sensible, but it's wrong because it leaves out the capital cost of the heating equipment. Of course, as you add more insulation, the marginal cost of saved heat goes up more and more steeply until you reach that supposed cost effectiveness limit, and then you have to stop. But we kept going another several-fold in order to eliminate the heating system, and then the cost plummeted again to $1,100 less than normal because we didn't have to pay for the furnace, ducts, fans, pipes, pumps, wires, controls, fuel supply arrangements. In other words, the key to a cheap building was expensive windows. Get to that in a minute. But first, the building has to be airtight and super insulated. It's airtight originally to the same degree as a modern passive house, that is about a palm of your hand size area of uncontrolled air leakage, thanks to very good caulking, double weather stripping, rubber sweeps that drop down out of the exterior doors to seal against the threshold, which itself has a thermal break when you close the door. The building is super insulated. Maybe we can get a glimpse in there if, yeah, thank you. So yeah, you can see there's 10 centimeters of polyurethane in the middle of these slip-form masonry walls. So 15 centimeters of reinforced masonry each side. And the outer masonry amplifies the insulation by storing some heat during the day that tempers the cold seen by the insulation at night. And then the inner masonry wall stores trapped heat that provides a comfortable radiant temperature that was actually stored months earlier. That is, the air and radiant temperatures are months out of phase with each other so that their average, which determines your comfort sensation, is smoothed out. And therefore, the effective insulating value of these sandwich walls is about 0.14 watt per square meter Kelvin. That is R40 in American units. The roof has very thick polyurethane, about 0.04 K or R80 plus. And so that's about 2 or 3 times what people normally use. And then we have twice the normal window area, and almost all of it faces more or less southerly. The whole house faces exactly south. I expect the archaeologists we built it for will probably surmise that it must have been a temple to some primitive solar cult. But the windows are unusual, and they're now 5th generation. They're better than we started with by a factor almost 3. You can see in the window frame that there are 2 grooves, each of which carries a 50 micron polyester film, and each film is coated on both sides with a magic, almost atomically thin multi-layer sandwich called heat mirror, which lets light through but reflects infrared. And then the 3 spaces inside are filled with xenon, which insulates 3 or 4 times as well as air. Many people use cheaper krypton that insulates twice as well as air. And if it's too thick a gas cell, you'll get too much convective heat loss. If it's too thin, you'll get too much conductive heat loss. So you have to pick the right spacing between the films. But when you do that, these windows turn out to be as insulating as 16 sheets of glass. That is, their center of glass value, not counting edge losses, is a true R14 or 0.4 watt per square meter Kelvin. And for bragging rights, we have downstairs 3 units that insulate like 22 sheets of glass. There are 20 in the center, or K.26. You can, of course, tune windows to different directions to control separately the flow of heat and light into the building. RMI's nearby office does that. But if I had to pick one technology that makes this building work as well as it does, it would be these super windows. However, as you'll see, that's part of a system design. It's not just about a component. Now, this hallway was originally very dark, especially compared to the bright banana jungle beyond. And to make it less dark, we put in a skylight, but not right through the roof, which could cause leaks, but instead we borrowed light from the adjacent utility room. And that turned out to be rather straightforward. We used light tubes, which look like a duct except they're very shiny on the inside, and the light to squirt out into the hallway is gathered by Fresnel lenses up on the roof, because these light tubes bend up and go out through a board that we used to steal a third of the clear story area, the glass area up there, that heats our clothes dryer. You're looking in the clothes dryer. As Judy is showing, there are these metal bars in a device she found on the web. I guess it's to hang clothes over the bathtub in your Brooklyn apartment, like this. So you just pull your wet clothes up into the hot air that is created by sunlight coming in and hitting the dark paint. It gets so hot up there it melted a plastic fan hood. And also some of the heat for that clothes dryer comes from our router and switch and so on, our IT equipment, including these 3 gray boxes full of monitoring equipment to measure about 300 data streams in the building, although that equipment actually uses a bit more electricity than the things we're trying to monitor, so we're going to find a more efficient solution. And here's a chart of what 3 other engineers and I found in several days, tracking down all the parasitic loads in the house so we can exterminate them when we get some time. Now, we do actually have a clothes dryer for the benefit of visiting soccer moms, but we very rarely use it. We just use the efficient washing machine underneath. So now, looking down the other end of the utility room, you see there's a 65 kilowatt hour industrial lead acid battery bank, and that is wired in parallel with a pair of 3 kilowatt SMA Sunny Island inverters. Those run all the critical loads, most of the loads in the house, all the time. with or without the grid. So if the grid fails, it keeps running, and if it's daytime, the inverters on the roof will keep on charging the batteries or wait till next morning if need be. So we think this gives us indefinite autonomy. The only power failure we've had in 25 years is when a cell failed in the battery bank, replaced by this white one, and we had to wait for the replacement and run on grid power meanwhile. But otherwise we have no power failures because the entire house is an uninterruptible power supply, whereas recently our neighbors had 8 power failures in one morning. We're up in the mountains where things happen. You can see a whole mess of pipes. What are those about? Well, that's about the thermal side of the house. Originally, that black pipe brought in propane for a demand heater that would add the last few degrees as needed, modulate down to 0, to give us the last 1% of our water heating, which was solar. And we also had a couple of wood stoves that did the last 1% of the space heating. And as we were thinking about the renovation, Judy said, why are we doing combustion? That's so 20th century. Let's stop burning stuff. So we figured how to expand our solar thermal system to do those 2 backup functions without having to burn anything. We went from 4 to 8 thermal panels on the roof and tilted them up from 40 degrees, enough to make snow slide off, to 70 degrees where they should have been in the first place, so they would not overheat in the summer but would give us more energy in the winter when we wanted it. Those thermal panels circulate antifreeze into a finned heat exchanger in the bottom of a 5 cubic meter super insulated storage tank up under our bedroom closet behind the stairs. That water's been sitting in there since 1983. It's a storage medium. It doesn't go anywhere. The warmest water, heated at the bottom, rises to the top and surrounds a copper coil. That's our water heater. And then we added a second one as backup space heater. And then the coolest water sinks to the bottom of the tank and gives those solar panels a better load to work into in the winter, so that makes them more efficient. But then how do we get that hot water from the secondary heat exchanger coil at the top into the radiant coils that we cast into the floor slabs in 1983 in case we might need them someday? And they weren't hooked to anything till 2009. They were stubbed out to the chase, the hollow trench with a wood cover that contains practically all our wiring and plumbing. So if we need to change or fix something, we just lift up the cover and there it is. We did that because, as Stuart Brand says, every building is a forecast, every forecast is wrong, so designed for flexibility, and I'm really glad we did. But those coils were still okay, so we hooked them up to the extra solar hot water to provide the last 1% of our space heating. So how do you get the heat from the secondary heat exchanger added in the top of that 5 cubic meter storage tank into the radiant slab coils for the last 1% of the space heat? Well, our master plumber said, I got just the thing. I'll get you a primary pump and 6 zonal secondary pumps. I said, well, 7 pumps, isn't that a lot of power? He said, no, it's trivial, 2.3 something kilowatts. I said, well, that's well over twice what the building uses for everything. Let's talk about efficient pipe layout. You see, the friction in a pipe goes down as nearly the 5th power of its diameter. So if you make the pipe a little fatter, you lose most of the friction, as we did, along with good insulation, so you can't really see how fat they are. We used electronic and manual full port ball valves, which almost eliminates friction when those are wide open. We used magnetic flow meters, again, to get rid of friction and moving parts. And we laid out the pipes in such a way that instead of bending at right angles with normal elbows and manifolds, the water can turn 45 degrees gently, go around sweet bends instead of sharp bends, and almost eliminate friction. And therefore, instead of 7 pumps, 2.3 something kilowatts, we have 1 pump, maximum 43 watts, 97% less friction. At the moment it's poking along at 6 watts, just waiting for something smart to happen. And that was a 97% saving in friction by laying out the pipes properly. If everybody in the world laid out pipes and ducts to be fat, short, and straight instead of skinny, long, and crooked, it would save about 1/5 of the world's electricity. That's about half the coal-fired electricity, and pay back typically in less than a year in retrofit, instantly in new build. So why isn't this in any but one engineering textbook? Why isn't it in climate models, government studies, industry forecasts? Because it's not a technology, it's a design method. And most people don't yet think of design as a scaling vector, a way to make things big fast. So we have a lot of work to do and a lot of opportunity. Now let's go back out here. I won't take the time to show you all the efficient screen outputs here of the various data we're monitoring. There's a whole bunch of energy books I wrote over here, lit up by little 1/10 of a watt LED lights. There's also this dude from Papua New Guinea and other dude from Papua New Guinea. I can't resist showing you this wonderful silk thread embroidery by Mo Mei-Yun, a grandmistress of an institute she founded to revive this nearly lost 1,200-year-old art. But quite amazing how the light changes when you move. This took her 27 days. It's one of her minor pieces of work. Now let's go into the kitchen and see what integrative design and efficiency do there. Now, the stainless steel thing straight ahead is our New Zealand refrigerator and drawer freezer. And had you been here about a year earlier, you could have seen the oak veneered 32-year-old model, which finally got capillary plugs we couldn't fix. So we had to retire it and get this nearly as efficient modern model that's industrially produced. The original one was a handicraft. But the original one used 8 to 15% what was then the normal amount of electricity, because it had very thick insulation, good seals, as this also does, but it also had the compressors up on top so the heat wouldn't rise up into the food again. And if we go back into the pantry, we can see the remains of, just tucked up there, a little insulated copper tube which ran uphill from the old refrigerator, this one doesn't have that feature, to the outdoor fin that you saw outside the front door. What is that for? Well, that's a heat pipe so that when it's cold enough outside, which is about half the year, the chlorine-free refrigerant simply condenses in that fin, runs down by gravity, and the thermostat controlled compressor stays off because the cooling's already been done. We actually could make this unit about 2 or 3 times more efficient if we have the right partner to work with, so I'm still looking for that to do vacuum insulation and a little sharp helium Stirling engine instead of what's there now, but this is still a very good unit. Now, over on the other side of the kitchen, this Swedish dishwasher from Asko looks quite ordinary, but it's smarter than most because it has sensors that look at the outgoing water for grease and turbidity, and when the water comes out clean, the dishwasher will move on to the next step or stop rather than running on a clock. That saves about 2/3 of the water and the water heating energy. We are, by the way, plumbed for gray water, so if Colorado ever figures out the rules, we'll be able to sand filter it under that outdoor garden and irrigate the garden and the pasture, maybe get a little extra hay from, maybe an extra month from the warmth and the nutrients in the gray water. Up above the stove is a Mitsubishi air-to-air heat exchanger recovering 3/4 of the stove heat into fresh air that then comes out the top. Although I had to improvise a little condensate drain because they didn't design for a climate quite this cold. The cooktop itself is from Conduction AG in Basel, invented by Duško Marović, a Croatian engineer. Let's do a little science experiment. Thank you, Judy. So we're going to turn this on and see what happens. We'll just crank it up. The Celsius indicator on this old hob, this is first generation technology, is no longer accurate. We're about to get a whole new cooktop 5 generations later that will be highly accurate. But the hob itself is a high-tech ceramic called silicon nitride. You can scratch it with a diamond ring if you want. And you can actually fry right on it if you want and then easily wipe it clean. But it's electronically controlled in such a way that of these 4 hobs, only one runs at a time, typically with a 1 or 2 second pulse of power. And therefore, the whole device only draws a peak of 2, or if you have big burners, 3 odd kilowatts. So you could actually run it off a normal 117 volt circuit, which makes it easy to retrofit a gas cooking or gas heated house without having to put in 240 volts. Now normally when you heat a cooking pot, the bottom tries to expand, but it can't get bigger because of the sides, so it warps. And the American test procedure doesn't notice, but the German test procedure says that makes it 3 times less efficient than a clever design like this. Now they have even simpler ones that Duško cooked up so that it stays perfectly flat in full contact all over all the time. So tripled heat transfer efficiency, and he's about to send us his new generation of pots, which are vacuum insulated, and so is the lid. That again doubles the efficiency. So when you put together the better pots, the power electronics, the sensors, the software controls, the flat bottom, altogether, it's a lot more efficient than the next best induction cooktop. In fact, without the vacuum pots, this was just measured at 2.5 to 4 times more efficient than induction. Now, we're just starting to boil, and if at this point I decide I want to do, say, hard-boiled eggs, which at this altitude is 10 minutes, then I just press the button, set it on 10, press it again, and walk away, and it will now hold that desired temperature within a few degrees for 10 minutes, and then it'll beep and turn off, and each hob has that intelligence. Each hob has child safety features and so on. So digital cooking is a whole lot different. And in fact, if you were cooking in a vacuum pot, you would only give it 1 second of pulse power every 50 to 60 seconds because it's losing almost no heat. And then it is enormously more efficient, not just 4 times more efficient than induction, but normally 2.5 to 4, and then even better with the vacuum pot and lid. So this starts to give us some hint of what's possible. We have, I think, good, but there's no real standard or test procedure to tell us, microwave and oven. The oven could be probably a lot better. And countertops made of recycled countertops. Let's go out this way. Oh yeah, we did. Thank you, Judy. We switched from fairly dark oak cabinetry to light maple finish, with several layers of LED lighting, and it makes the kitchen enormously brighter and more cheery, just by having lighter surfaces to bounce light around better inside the space.
We have about 85 watts of lighting in here. Could be 1 light bulb, but you can see under the shelves.
Yeah. nice layers of light. In these fixtures, each of the 3 little dots is 1 watt, and it's, again, very warm, accurate, pleasant color. By the way, just wanted to introduce you to my little Bornean granddaughter, Kessie, at 4 or 5 months. And over here, a painting by our late bonobo friend, Pambanisha Wamba. She said it was 3 of her favorite things: blueberries, eggs, and Perrier. And she painted it as a thank you present for our having helped design their house in Des Moines. And we put these bonobos on the team because they've been co-reared with people for several generations, so they understand probably several thousand words of English. They're extraordinarily smart. They're good designers, so we put them on the team and did interspecies design, which is quite a trip. Now, we come next to what would normally be the furnace of the house if we had one. We actually did have, pretty much where I'm standing, another wood stove, which has now been removed, and I want to turn this leftover flue into a light tube to get a little more daylight in here. But what would be the furnace, what gives us the control margin in bad winter weather, is this interior jungle of 85 square meters with over 100 kinds of higher plants. And there's a lot going on in here, at least 7 kinds of energy collection. So let's start with the heat that comes in through the super windows. Do not try this at home, kids. Overhead glass will roast you at sea level, but at 2,200 meters elevation, it always gets cold at night, even in the summer, so we can always night flush. And in fact, to keep it from getting hot and glary on the south, despite the super windows blocking about half the incoming energy, but cold and dark back on the north, we make this arch, cantilevered arch holding up the middle of the building, in such a shape that in the winter, the low-angle sun skims all the way to the back and hits the top of the bathroom door. But in the summer, the high-angle sun comes right down and the hot air rises up and is confined in the back of the arch. And then we just open up any or all of the 3 high vents that are open up there at the back. Those are controlled simply by ropes leading down to boat cleats at the front. And you can also see that we can open any or all of the south windows and let it stack cool like a chimney so that it doesn't overheat. And the sun that comes in is hitting this nice organic soil. A lot of it gets into the slab or the soil under the slab, because we don't insulate under the slab. You probably would now, but in those days it didn't seem to matter. So we just ran a skirt of side insulation down a couple of meters all around the house, and therefore got a lot of extra coupled thermal mass. And we figured if we coasted on the stored heat in a total eclipse in January, we'd lose about half a Kelvin per day. So that's heat. Now, another kind of energy collection is light, which comes in, of course, from windows facing in many directions in the various rooms of the house. Only the bathrooms lack daylight. And the light is also bounced all over by that cloud photograph-covered tiltable light shelf you see in the back, by the white joists, by the white plaster. It was originally maybe 96, 97% daylight, now maybe 80-odd, with the jungle blocking some of the light. It's not sophisticated daylight, but it's pretty good. And at the moment we have lights on to help with the filming, but actually we don't normally use them in the daytime. Now, another way we collect energy here is as hot water. Up in the back of the jungle, there is this white-looking wall. It's actually gray in the near-infrared that sneaks through the glass. And under the vents cast into that wall, there's 100 meters of plastic tubing that preheat water before it goes up to the coil in the top of the stratified tank to get the rest of its solar heat. So a good deal of the water heating is actually done passively in this wall. And also you see at the back of the jungle those two blue painted ducts sticking up. Those are to using this whole atrium as a giant hot air collector, sucking the hottest air down from the top to go into the air-to-air heat exchangers up above the bathroom door, you can see there, so that 80-odd% of the heat that would otherwise escape in the stale air we're exhausting from the house actually gets recovered to preheat the incoming cold, dry air. Now, when that happens, we also recover the condensate that drops out when the warm air goes past, but separated from, the cold, dry air in. Condensate drops out, we recover it, and we feed it into a waterfall, a pond running down a stream to another pond, and that way we always have this supply of distilled water. So we are recovering not only the water itself, but the latent heat of evaporating it, the negative entropy of mixing, that is the energy you would have to use to distill it if you didn't already get that for free. As you see, we have a bunch of happy fish in both ponds. And the waterfall has a lot of reasons, of which the most fun is as an acoustic mask, because of course with 40 centimeter stone walls and heavy gas-filled sound-blocking windows and no mechanical systems to make noise, the house is utterly silent, and it would be really distracting to hear every conversation. Now, the waterfall used to be higher than it is now, but it still makes a very pleasant sound, and that's largely because the day we were doing the masonry, this Japanese gentleman mysteriously appeared. It turned out he was a professional waterfall tuner, and he was there to make sure that our splash pattern was in the pleasant, soothing alpha wave frequency range instead of irritating beta wave. So we adjusted the rocks and made it splash with a pleasant sound and went away. I don't know who he was, one of our angels, who just happened to know to come that day. Now, the distilled water also enables us, of course, to do subsurface drip irrigation. So instead of feeding weeds on the surface, we just feed the root zone and flush any salts down below it so we don't salt the soil with our very hard local water. And the reason we have two fish ponds is partly so that if one of them crashes, like if the bubbler fails while we're out of town, we can reestablish from the other one. It's happened a few times. And the clam larvae and crayfish larvae and fish fry and so on can go back and forth between the two ponds. Now, the seventh kind of energy collection is photosynthesis. And Judy is holding a picture of how that works here. As you can see in the banana jungle, you can grow really big earphones. This is a double banana crop from one of our 6 banana trees. And if all 6 fruit at once, that's the banana emergency for which we need the orangutans. But there are actually over 100 kinds of higher plants. So on the left here, we're doing a fig. There's charred kale, basil, kitchen herbs, all sorts of stuff here. In the front, Yeah, there's the basil, nice pesto. Let's see. We have here one of our Bornean sugar palms, the strongest known wood and fiber, highest known optical leaf efficiency, 10 times as productive as sugar cane, 55 known uses in Indonesia. Incredible tree, Arenga pinnata. And let's see, over here, from left to right, those trunks are avocado, pineapple, guava, cinnamon with the shaggy bark. Then we get into some various sizes of bananas. Oh, here's a little lime just come out. There's some elephant ear, pineapple, a bunch of rosemary. That's another bigger sugar palm there next to the Bornean mahogany with the compound leaves. The purple thing is a Bornean tribal boundary marker because it doesn't go anywhere and has a unique color. Over here is a babaco, which is a natural papaya hybrid, and it's actually regrowing for the second time after the trunk actually broke off from the weight of the fruit. Nice problem to have. But back here there's a bunch of ginger, there's coffee with some beans on it. All sorts of things like to grow here. And we actually arrange these chairs so that you can lean forward for papayas, or once we get our new mango tree in, backward for mangoes. And it's nice to do that while it's blizzarding outside and know that you're not using anything up or stealing from your kids. Behind that curtain on the left is a Lazy Susan for our agricultural and fish materials. We actually were foolish enough to put the Lazy Susan in after framing the aperture, but it fitted with a millimeter or two to spare, so we were lucky. There's a little household office. Then there's a bathroom, which originally just had a 3-liter Swedish toilet, but now Toto has given us this Japanese toilet. They use this commonly to save space. You notice there's a sink at the back so that when you are washing your hands after using the toilet, you are filling the tank with gray water and thus cascading water to lower quality use. And then we have an efficient hand dryer from Dyson, usual quadruple efficiency shower heads. Sloan gave us a waterless urinal for the guys and a solar valve that doesn't need wires or batteries. And another of Judy's beautiful images of the Tetons is lit, as you could see if the other lights were off, by only 1.5 watts of LED with a thin film optical lens that turns a round blob of light into a rectangle the right shape, and it's next to another air-to-air heat exchanger. There is also a fourth pod in the back. These cylinders of poured concrete don't need much concrete. They can do quite a thin shell to withstand a big sideways thrust load from the backfill. This one happens to be a kind of library reading nook, and it has a very high ceiling with only 34 watts of LEDs, but the optics are so good that you have great reading all over. And now we're down here in the big energy library where we originally had a double row of desks down the middle and where RMI was hatched for 18 years. Judy now has her studio here. She's a fine art landscape photographer and does her photo printing here. judyhill.com if you're interested, and some of my work's up there too. This is one of mine from a reflection in front of the German Foreign Ministry in Berlin. And Judy mounts an art gallery here with little magnets on a curved piece of steel. These are some images we both made in a recent trip to Iceland, a very beautiful place. This little wing also has sextupled efficiency fans from the late Paul McCready, and you get a factor 3 efficiency gain on the airfoils and factor 2 on the motors, and then more on controls. This is post and beam construction, and the posts are Colorado red spruce, beetle kill. It has the nice property that the bark doesn't fall off. As you go from the north to the south, you notice these 6 by 12 inch oak purlins holding up the roof get further apart than they were back at the north because they're shorter. So you don't need them so close together to hold up the same roof load, which is calibrated for earth sheltering. And also, any civil engineers might notice that the 16 by 12 inch master beam holding up those purlins has its stair-step joints to distribute stress not over the posts, which is traditional, but where they should be at the 0 moment points where the beam isn't bending. We do have, you notice, one wood stove still here. It hasn't run since 2009. I don't think it ever will. It's there for emergencies and decoration. And there's one more bit of technology I want to show you, going past the loft where I have 3 big screens for serious writing. We can go down here, more library, lots of files of my 700 odd publications and others. And back here is a technology from Germany where there are over 1,000 certified components for passive houses. This is one of them with a dealer in Minnesota. You can see the thickness of this door, but you might be surprised that it actually insulates like half a meter of polyurethane because there are vacuum panels inside. And this is also one of those pieces of glass that insulates like 22 sheets of glass. We also had the outside made in steel to help keep the bears out. And there are 2 weather strips, one on the door and one on the jamb. So it is extremely airtight and closes a bit like a bank vault. And actually, if we zoom, we can probably see all the way up to the Continental Divide, which is just, well, it's a little cloudy up there, but it's up in that notch. And at any rate, you can see the window, despite its extraordinary insulating value, is perfectly clear. Now, I've shown you a lot of technologies. There are more, but let's stop here. But I'd like to emphasize how they're all put together, how they're chosen and combined in what we call integrative design. First, there's the whole concept of making the building so efficient it doesn't need heating. You do that mainly through costly windows, but the whole building gets cheaper. And there are also many benefits from each expenditure. So this cantilevered arch holding up the middle of the building has 12 functions, but only 1 cost. Or if you look at the way the walls are curving in and out, they're undulating. Why is that? Well, I like to be able to control the place and angle at which sun and solar light and heat come in, so they get distributed properly. I get more torsional strength and stiffness from less material if the wall recurves like this. I can use a single set of forms for the slip forming and flip them upside down if I want the opposite curvature. There's better aesthetics. better acoustics, better exterior aerodynamics with less heat-robbing turbulence, and less likelihood of whistling at you on a windy night. So there's about 8 or 9 reasons. The walls are this shape, and we could spend days going through everything in the building. I don't think there's anything with fewer than 3 functions. 5 to 8 is fairly normal. Now, if you were physically in this building, you would experience a great sense of calm and well-being. And part of that, of course, is that you're always looking at the jungle, sight, smell, oxygen, ions of all those plants. But there are a lot of other features too. You have clean air. We designed out toxins in both building and maintaining. You have high radiant temperature, low air temperature, medium humidity. That's a healthier, more comfortable combination than hot, dry air. And almost no 60 hertz electromagnetic fields for what that might do. Natural light, which we're designed for. You can start to make a list like this that was kind of heretical at the time in '83, but now is pretty well accepted as how you would sensibly design a building to help people feel better. But there's one more subtle layer. I mean, just the obvious features we noticed would keep our Board of Trustees meeting around the dining room table in those days happy and alert all day, and the same people would get dozy and irritable in half an hour in an ordinary office. But there was more to it than that. And in this room where Bill Browning invented the whole concept of green real estate development, many things happened in this room, he got interested in a concept called biophilia, a hypothesis of the Harvard biologist E.O. Wilson and the late Yale architect Steve Kellert, who thought that people have a natural affinity for nature, for the life process, and if you embrace nature, bring it into the design, put it all over the building like this, you would have happier, healthier, more productive people. And Bill found what the science tells us is there are 14 things that people wanted to see when we were growing up on the savannah. So if we come up here to the scenic center of the house, where you can actually see all the way the right light from the clear story at the far west end to the top and bottom of the tree at the far east end, you notice that we've actually, by luck and intuition, checked 9 of the 14 boxes before the theory existed. The first thing you notice is what landscape architects call prospect, which is a long view downward. If you're a little biped out on the savannah with big cats that want to eat you, it is very valuable to have that long view of both predators and prey. We have a source of water. We have visible sources of food. We've had 77 banana crops so far. Right now we're in between a bunch of things, but normally there's 4 to 6 kinds of fruit hanging on the trees here. If the lion shows up, there's a place of refuge. You can duck into the cave. There's a sense of mystery, what's around the corner. Anyway, this was a pre-theoretic, intuitive biophilic building. And by the way, all of the extra things we did for a 99% saving on space and water heating energy, 90% on household electricity, which originally was $5 a month for 372 square meters before we went solar. Now it's negative. Saving half the water. All those savings paid for themselves in the first 10 months with 1983 technology. Today's technology is better and cheaper, and we're measuring to see how much better and cheaper. I hope this will give you a little idea of what simple materials and beginner's mind about design can do. We'd never built a house before, so we didn't know that what we were trying to do was impossible. That made it possible. We had wonderful help from a small number of design and construction professionals, but this was mostly built by college-age volunteers, including about a third of our spring '82 Dartmouth class. And I hope that some of you will have as great an adventure as we had with this one. I hope that's enough to give you an idea of how passive solar banana farming in the Rockies works, and I look forward to hearing what's on your minds. Thank you.